Section 1.7 is finding the inverses of functions. So first I want you to start out by sketching the graph of f of x equals x squared. Not a v. Okay, the parabola. So, all right, there's our rough sketch of y equal x squared. That's f of x. Is f of x a function? Yes, why? How do we know? Okay, so yes, it passes the vertical line test. Now, to find the inverse of a function, we have to swap x and y, then solve for y. So that was the equation y equals x squared. So we have to swap x and y within that equation. So instead, we're going to have x equals y squared, and now we have to solve that for y. So what's the first step in solving it? Square root both sides. Now when you square root a variable, what do you have to remember on the other side? It's either positive or negative. Positive or negative, because a positive square root of x squared would give us that. A negative square root of x squared would give us that. So y equals plus or minus the square root of x. The notation for an inverse is denoted by f with a little superscript of a -1 of x. So we read that as f inverse of x. Okay, so the notation for an inverse, f inverse of x with a little -1 is a superscript. Therefore, for this particular equation, f inverse of x equals plus or minus the square root of x. So now we need to sketch the graph of f inverse of x. So the square root graph, positive square root of x looks like that. What is negative square root of x? What does it look like? The other way down below. Okay. Now the question is f inverse of x a function? No, because it fails the vertical line test. It fails the vertical line test. So we say that f of x does not have an inverse because f inverse of x is not a function. So your basic parabola, y equals x squared, it actually does not have an inverse function because the inverse fails the vertical line test. Now, what if I told you we actually know that just by looking at f of x? We actually know just looking at f of x that it's not going to have an inverse. Okay? So just by looking at it, we'll know f of x would not have an inverse because f of x is not what we call 1-to-1. Now, what does it mean to be 1-to-1? Well, first of all, in order to be one-to-one, it has to pass both the vertical line test and what we call the horizontal line test. The horizontal line test works exactly the same way as the vertical line test. It's just instead of having the pencil moving across vertically, you turn your pencil horizontally and move it across the graph. So if you have a horizontal line, let me create one real quick. Okay, so here's my horizontal line, and I pass that horizontal line over my parabola, x squared. It fails the horizontal line test because it is crossing at more than one spot on that graph. Okay, so each x has only one y, and each y has only one x. So none of the domain and range values ever repeat. One-to-one. Each x has only one y, each y has only one x. It has to pass both the vertical and the horizontal line tests. So, as a summary, a function will have an inverse only if it passes both the vertical line test and the horizontal line test. Okay. Example 1. Given the function f, okay, and we're given the function as a table of values, we need to sketch the inverse function, f inverse of x. Well, first I want to start by sketching f of x and plotting these points. So we're plotting the point -3, -2, -5, -3, -1, +1, and 0, 3. Now, can you see how that's kind of curved? All right, so we need to draw that curve. Now, up above, when I said we need to find the inverse, I said we swap x and y. So when you have a table of values, you have the coordinate -3, -2. On the inverse function, that point is flipped. Okay, so we're swapping those columns. So on my inverse graph, f inverse, instead of the x being -3, that's my y value, -3. And instead of the y being -2, that's my x value. So on my inverse graph, I'll have the point -2, -3. So let's plot that one, -2, -3. Then the next point was -5, -3. So on the inverse graph, what would it become? -3, -5. Let's plot that point. Then we have the point -1, 1. On the inverse graph, that would be 1, -1. So 1, -1. And then the final point, the original graph was 0, 3. So on the inverse graph, it is 3, 0. So we can now see the curve there. So let's draw it in. now look at those two curves, f of x and f inverse of x. Do you notice anything? What do you notice? It's a reflection. It's a reflection over what? The diagonal y equal x. So with your pencil, I want you to draw in a dashed line representing y equal x. So the diagonal line y equal x, we draw that in. And we can see the inverse function is a reflection of the original function over that line y equal x. If you took your paper and you folded it over the line y equal x, you'll see they match up. Okay? So in the little bubble down below, we're going to write in the inverse graph is a reflection of f of x over the line y equals x. Okay. All right. Questions? Yes. Mm-hmm. Okay, anytime you take the square root of a variable that was squared, then on the other side, the square root, you always have to put a positive and a negative in front of that square root every single time. So if we had x squared equals 4, and to solve that, you square root both sides. Because I'm taking the square root of an x squared, a variable squared, that x equals plus or minus the square root of 4, which means x equals plus or minus 2. Okay? Because if I take a positive 2 and plug it in for x and square it, I get positive 4. If I take a negative 2 and plug it in for x and square it, it gives me a positive 4. Okay? So the other side, whatever the square root is, you always put plus and minus in front of it. Okay? Other questions? Mm-hmm. Correct. Well, I'm doing negative 2 quantity squared. So the negative gets squared first. A negative squared becomes positive, and it gives us the positive 4. Okay? But you're right, if you had square root of negative 4, that gives you an imaginary number. Other questions? Okay, next page. Example 2. Graphically determine whether each equation has an inverse. If it does, find the inverse function and state any restrictions on its domain. Okay, do y'all have calculators? Pull out a calculator. Okay, so the first function we need to type in, f of x equals 4x to the 5th minus 8x to the 4th. So 4x to the 5th minus 8x to the 4th. I'm just going to do Zoom 6 to put it at a standard viewing window. Okay, so just looking at the graph, how are we going to tell if this function has an inverse? Has to pass both the vertical and horizontal line test, does it? Which one does it fail? Horizontal. Okay, we can take our pencil, hold it vertically and run it across and it passes. But once I put it horizontally and move it up and down the graph, we'll see it hits the pencil sometimes 3 times. Okay, so fails the horizontal line test. So no inverse. Fails the horizontal line test. Okay, so now let's look at the square root of x minus 4. Okay, what about this graph? Does it have an inverse? Passes the vertical line test? Passes the horizontal line test? Yes. Okay, so yes, it has an inverse. So now that it does have an inverse, we have to find the inverse function. And we have to state any restrictions on its domain. So what is it that I do with this original function to be able to find the inverse function? Switch x and y. So instead of y equals square root of x minus 4, it's x equals the square root of y minus 4. Now what do? Square both sides. So x squared equals y minus 4. Add 4. So y equals x squared plus 4. That is the inverse function. So instead of y, I'm going to put y inverse to show that that is the inverse function. Or we could write it as f inverse of x equals x squared plus 4. Now, let's think about this. X squared plus 4, what would that graph look like?
It will be the 4 units.
All right, so it's your parabola moved up 4 units. Now it's the entire parabola. Well, if I reflect that over the line y equal x, does that give me the square root of x minus 4 graph that we just looked at?
No.
Doesn't it give me extra? Gives me extra. I can't have the entire parabola as the inverse function, which is why we're going to have to restrict the domain. We have to restrict the domain. Okay? Look at the square root of x minus 4 graph, and I want you with that graph to tell me what is the domain of that function. Good, 4 to infinity. What about the range of that function? Low to high. Good, 0 to infinity. Well, your domain always deals with which values, your x's or your y's? X's, and the range deals with your y's. Well, remember when we found the inverse, we did what to the function? We swapped x and y. So guess what? When you're looking at the original domain and range, the original domain dealt with your x's, the original range dealt with your y's. So when you find the inverse and you swap x and y, you're swapping your domain and range as well. So the original domain becomes the range of the inverse, and the original range becomes the domain of the inverse. So this restricted domain for this parabola, x squared plus 4, is what the range was. 0 to infinity. Okay, so we might want to write that down. Swap the original domain and range to find the restricted domain of the inverse. Okay, does that make sense? Because we swapped x's and y's, so since the original domain dealt with the x's, that now becomes the range dealing with the y's of the inverse. Let's look at a second one, C, or a third one. F of x equals x minus 1 divided by x plus 2. So on the calculator, let's graph that. So I have a fraction, so alpha y equals, pull up my fraction, x minus 1 divided by x plus 2. And graph. Will this function have an inverse? Does it pass the vertical line test? Yes. Use your vertical line, your pencil. Now turn it horizontally. Does it pass the horizontal line test? Yes, it does.
Yeah.
So this one does have an inverse. So yes, it has an inverse. Okay. So to find the inverse, we're going to swap out the x's and the y's. So we'll have x equals y minus 1 divided by y plus 2. And now we have to solve for y. Okay, well, on the right-hand side, do I really want the fraction? So what can I do with that denominator? Multiply it on both sides. That helps get it out of the denominator. So I'm going to multiply both sides by y plus 2. So on the right side, they cancel out. On the left side, y plus 2 times x, I need to distribute the x. So x times y plus x times 2, which is 2x, equals y minus 1. Well, I have to solve this for y, and I have more than one y in this equation, which means anything with a y in it, I have to put on one side, and if it does not have a y, I need to put it on the other side. So what should I move? I don't have just an x up there. Okay, I need to move this y, so I need to subtract it from both sides. So I have xy minus y plus 2x equals negative 1. So again, anything with a y is on one side, but if it does not have a y, it needs to be on the other side. So what else should I move? The 2x minus 2x. So xy minus y equals negative 2x minus 1. Okay. Let me just rewrite that over there. That was from the other line that we wrote. Okay, so here's where we're at. Look at this side with the y's. I now have two terms, and they both have y in common. So that is their greatest common factor, which then means we have to factor it out. I have to factor the y out of both of those terms. So when I factor the y out of the first term, what am I left with? When I factor it out of the second term, what am I left with? Minus 1 equals negative 2x minus 1. Now, solving for y, getting it completely by itself, means I'm dividing both sides by x minus 1. So y equals negative 2x minus 1 divided by x minus 1. That is my inverse function. So with the y, I'm going to put that superscript of negative 1. Okay, question? No. As long as the y's are together. Doesn't matter which side you move them to. Okay. Well, now we have to come up with our restrictions on the domain. So look at your calculator. Look at that original function. The original function was x minus 1 divided by x plus 2. What's the original domain of this function? X cannot equal what? Negative 2. So it's all real numbers, but x cannot equal negative 2. Now looking at the graph, let's figure out the range. Cannot equal, what number is this right in here? That is a positive 1. Correct. So the range is all real numbers, but y cannot equal positive 1. That's the original domain and range. So which one of those becomes the domain of the inverse? The range. So instead of that being y does not equal 1, on the inverse that becomes x does not equal 1. So the restricted domain is all reals, but x cannot equal 1. Now look at your inverse function. What's in the denominator? X minus 1. So what happens if x equaled 1? 0 in the denominator. That's exactly right. Okay. All right, questions? You should always look at the original domain and range of the original function, just to be sure. Question? Yes. You can always use interval notation. Yes. Not required. Okay. Example 3. Given the function f of x equals x plus 3 divided by 4, are there any domain restrictions? Look at that. X plus 3 divided by 4. Think about how you could write that. 1/4 x plus 3/4. What would the graph of that look like? Is it a parabola? Is it a circle? Is it a cubic? What is it? It's a straight line. Okay, it is a straight line. So will every straight line, a linear function, will it pass both the vertical and horizontal line tests? Yes. What's the domain and range of every linear function? All real numbers. So will we have any domain restrictions on this graph? No. No domain restrictions. Domain and range equals all real numbers. Okay, so we had y equals x plus 3 divided by 4. Now we have to find the inverse, which means we swap out x and y. So x equals y plus 3 divided by 4. Multiply both sides by 4. So we have 4x equals y plus 3. Subtract 3 from both sides. So y equals 4x minus 3. That is the inverse function, so I put the notation with the y inverse. And the domain is all real numbers. All right, any questions on that? Okay. Yes. Oh, up here, no common denominator. It's just x divided by 4 plus 3 divided by 4. X divided by 4 is the same as 1/4 x. Okay, Dwayne? So the range of this inverse is going to be what the original domain was. The range of this inverse would be all real numbers, but y cannot equal negative 2. Okay, both of those just get completely switched. That becomes my domain. That becomes my range of the inverse. Okay. Any other questions? All right, then we can flip it over. Now let's say you have just two functions, and we have to be able to confirm algebraically that they are inverses of each other. To do that, we use composition of functions. We have to do f of g of x and simplify it all the way down. And we have to do g of f of x and simplify it all the way down. And when we do both compositions, if they both simplify all the way down to x, then that proves they are inverses of each other. Let's give this one a try. Confirm your answer to part A in example 3. So our last function, f of x, was x plus 3 divided by 4. And the inverse function that we found, f inverse of x, equaled 4x minus 3. To keep it in terms with our composition of functions notation, f and g, I'm going to call the inverse function is my g of x. Okay, so first I need to do f of g of x, which means I'm doing f of the g of x function, which is 4x minus 3. And that means 4x minus 3 is placed into the f function wherever there's an x. So because there's an x right there, I'm going to plug in the 4x minus 3. So I'll have 4x minus 3, then I finish it off, plus 3 divided by 4. Now we simplify. Negative 3 plus 3, those cancel to 0. So I have 4x divided by 4. The 4's cancel, and we're left with x. So that one worked. That simplified all the way down to x. Now we need to do g of f of x. So that means g of the f function, which was x plus 3 divided by 4. So into the g function, which is 4x minus 3, wherever there's an x, I plug that in. So I start with the 4, then in parentheses, for the x, I plug in my function f, x plus 3 divided by 4. And then on the end, I have minus 3. Always important to remember PEMDAS, order of operations, parentheses, exponents, multiplication and division, and then adding and subtracting. So parentheses, inside the parentheses cannot do anything. No exponent, so now I look at the multiplying. 4 times x plus 3 over 4. What happens? 4's cancel, so we have x plus 3 and then minus 3 on the end. Plus 3 minus 3 cancels, so we are left with x. That simplified to x. The first one simplified to x, so that proves they are inverses of each other. They are inverse functions. Questions on that? Okay. Example 4. Example 4 says determine algebraically if f and g are inverses. F of x equals x squared over 4 plus 8, but only when x is greater than or equal to 0. And g of x equals the square root of 4x minus 32. So, f of g of x. means f of, my g of x function is the square root of 4x minus 32. So that means I'm plugging square root of 4x minus 32 in for x in the f function. So my f function was x squared. So in place of the x, I plug in the square root of 4x minus 32, quantity squared, divided by 4, plus the 8. I have square root of 4x minus 32, quantity squared. So what happens? They cancel. So up top I have 4x minus 32 divided by 4 plus 8. With 4x minus 32 divided by 4, can I divide the denominator of 4 into both of those in the numerator?
Yes.
Yes. That's 4x over 4 minus 32 over 4. 4x over 4 is x. Negative 32 over 4 is negative 8 plus 8. The negative 8 plus 8 cancels. We're left with x. That one worked. Let's try the other. G of f of x. So it's g of x squared over 4 plus 8. So go to the g function, which is the square root of 4 times, instead of x, we plug in the f function, x squared over 4 plus 8. Finish off the g function, which said minus 32. All right. 4 times x squared over 4 plus 8. I need to distribute that throughout the parentheses. So 4 times x squared over 4 is x squared. 4 times 8 is 32. Bring down the minus 32. 32 minus 32 cancels. So we have square root of x squared. And what is the square root of x squared? X. That works. So they are inverse functions. Questions? Yes, Deja. Uh-huh. Okay. Right here, when I multiply 4 times x squared over 4, the 4's cancel. 4's cancel, we're left with the x squared. Okay. Other questions? Okay. Next side. Example 6. Restrict the domain of the function so that the resulting function is 1-to-1. Then determine the equation of the inverse. Okay. As it is, what part does it fail? Horizontal line test. Where can I start restricting the domain of this function so that it won't fail the horizontal line test? How about -5 right in there? So if I restrict the domain, oops, restrict the domain to -5 to infinity, then I'm only going to be looking at that portion of the absolute value graph. That portion, we're restricting it from the domain so that this portion of the graph will have an inverse. Okay? Now, if we're just looking at that portion of the graph, That's the positive portion of the absolute value of x plus 5. Okay, that's the positive value of that. So if we're just looking at the positive of that, then that's y equals x plus 5 minus 4, which is y equals x plus 1. Now, for a second, I'm going to erase all of that so that we can clearly see this graph. Does this line look like it's the line x plus 1? Yes, it has a y-intercept at 1 and a slope of 1, up 1 over 1, up 1 over 1. Okay? So that's my function with the restricted domain. So now I need to find its inverse. Finding the inverse, I swap x and y. So x equals y plus 1. Subtract 1, y equals x minus 1, and that's the inverse. Okay, questions? That's right, which left just this side, and if you look at that graph, it's linear, has a y-intercept of 1 and a slope of 1, up 1 over 1, up 1 over 1. And so that's the line y equal x plus 1. And to get that from the absolute value equation, because I'm only looking at the positive side of that, then when it has absolute value of x plus 5, I can just look at the positive value of that, which is just positive x plus 5 minus the 4. Okay? Generally, yes. That makes it easier. Yes. Correct. Correct. It may just say, look at this graph, does it have an inverse? And so you have to know, okay, either passes both the vertical line test and the horizontal line test, or it doesn't. So it'll be specific and it'll say, given this graph, restrict the domain and then find the inverse. Okay? Other questions? All right. The last example is guided practice, so that's the one you need to do on your own. I'll go ahead and tell you, it does have an inverse. You have to find it. Okay? Find the inverse function. X equals 3y divided by y plus 5. We need to get that out of the denominator, so we multiply both sides by y plus 5. The x is distributed, so x times y plus 5x equals 3y. If it has a y, it needs to be on one side. So I move the xy over with the 3y. So 5x equals 3y minus xy. The reason we do that is so that all y's are on the same side. They're both in common. It's a common factor that I pull out. Y times 3 minus x. Divide both sides by 3 minus x. So the inverse is 5x divided by 3 minus x. The restricted domain is all real numbers, but x cannot equal 3. Are there any questions on that? The original function, if you look at the graph, you'll see it has a horizontal asymptote at 3. You can look at this domain and see x cannot equal 3 by looking in that denominator.